Right. This next lesson is about enthalpy calculations and product and reactant favored reactions in thermodynamics. So the goals for this lecture is to be able to apply Hess's law to find the enthalpy change for a reaction, to know how to draw and interpret energy level diagrams, to use standard molar enthalpies of formation to calculate the enthalpy change for a reaction, to see how to measure and calculate energy changes associated with physical changes and chemical reactions, to identify the relationship between energy changes, heat, and work, see how we can determine whether a chemical reaction is product favored or reactant favored at equilibrium, and to see how we can determine whether a chemical reaction or physical process will occur spontaneously, that is, without outside intervention. So, enthalpy changes for an enormous number of chemical and physical processes are available online and in reference books and in the back of our textbook in an appendix. So this section is going to show us how to use that data. So Hess's law states that if a reaction is the sum of two or more of other reactions, the delta H for the overall process is the sum of the delta H values of those reactions. What does that mean, and why would we need to use this Hess's law? Well, let's look at an example. So enthalpy changes for a reaction can be measured by calorimetry for many, but not all chemical processes. For example, if we look at this equation, we have the oxidation of carbon to form carbon monoxide. All right, now, the primary product of this reaction, when I have carbon plus oxygen, the product wants to form CO2, not even CO. It wants to form carbon dioxide, even if a deficiency of oxygen is used. So as soon as carbon monoxide, or CO, as soon as this product is formed, it will react with oxygen to form CO2. So it's not possible to measure the change in enthalpy for this reaction by calorimetry because the reaction cannot be carried out in a way that allows CO, carbon monoxide, to be the sole product. So the enthalpy change for the reaction forming CO from carbon and oxygen can be determined indirectly from enthalpy changes of other reactions for which we do know delta H values that have been measured. This allows us to use Hess's law. The oxidation of carbon to form carbon monoxide can be determined indirectly from thermochemical data that's been obtained from two reactions that have been studied by calorimetry. These two reactions are right here. These are called our elementary equations. So what we do know is that carbon monoxide plus half of O2 react to form CO2. And again, remember, when we have these delta H values, our enthalpy values of formation, it's to form 1 mole of our product. If we look at equation, we're going to call this elementary equation 1 and elementary equation 2. We can see that carbon monoxide plus half of an oxygen gives me carbon dioxide, and I know the delta H for that. We also know that carbon plus O2 gives us CO2, and we know the delta H of this. Now, we can manipulate these two so that when added together, they yield the desired net equation. We call this our net equation. So down here we have our equation 3. This is our net. This is the equation that we want. Here's the equations that we know. How can we manipulate these two equations so that I get carbon plus oxygen to give me carbon monoxide? So what we need to do is, here I say, oh, I want carbon on the left. If I look at my two elementary equations up above here, notice I have carbon on the left in equation number 2. Great. So I'm going to leave equation number 2. I'm going to rewrite it down here just the same as it was because I'm going to do this here. I want carbon on the left, and equation 2 has carbon on the left. Let's look at our next piece on our net equation that I want. I want oxygen on the left. Well, if you look at equation number 1 up here, oxygen is on the left and oxygen is on the left. So I can't really go, oh, we're just going to pass on that one for a second. My net equation, I need carbon monoxide on the right. Well, if I go back up here and look at my changing colors, net equation, notice that carbon monoxide is in equation number 1, but it's on the left. I want it on the right. So we can manipulate equation number 1 and we can flip it. If we flip equation number 1, and notice that this is called equation 1 prime, if we flip it, which we can do, instead of having a combination reaction, it's just a decomposition reaction. So notice that I have CO is now on the right, plus half of an oxygen also on the right, and that my CO2 is now on the left. All I did was flip that equation. If I do that though, I have to take my delta H and flip the sign. So notice I went from negative 283 to positive 283. Now we just simply add up what's on the left and what's on the right and cancel out spectators. So hold on, we're going to get a different color here. All right, so when we want carbon, we have carbon that's going, there's no other carbons on the right that's going to cancel it out. So carbon's going to drop down to give me C. We're going to come back to oxygen here in a second. Notice that on the right side of my arrow, I have CO, which is going to drop down here. Now, why is there not CO2? Well, because I have CO2 on the left of an arrow and CO2 on the right of an arrow, they cancel each other out. Now, you might go, well, wait a second. I have oxygen on the right and oxygen on the left. Why is there not oxygen on the right in my net equation? Well, because I have half of an oxygen over here and I have a whole oxygen on the left. So, therefore, we need to find the difference. If I have half and a whole, this half is going to go away and leave me on the left with a half of an oxygen. So, I have carbon plus half of an oxygen to give me CO. That is my net equation. So then all we do to find my delta H, my enthalpy for this net equation, I just add the enthalpies of my elementary equations. And remember, we had to flip the sign. That was it of the first one. So we can just add these together now. Positive 283 plus a negative 393 to get the delta H for carbon plus half of an oxygen to give me carbon monoxide. So going back to look at our Hess's Law definition that says, if a reaction is carried out in a series of steps, the delta H for the reaction will be equal to the sum of the enthalpy changes for those individual steps, just like what we saw. And to do that, we manipulate the equation to get what we want on the left and on the right side of those equations. We add and subtract those reactants and products. What you do to the reactants and products, you have to do to the delta H value that goes along with that equation. Cancel what appears on both sides. Look for what is on the appropriate side and what needs to be canceled. Worry about the numbers last. So delta H is a state function, right? Either path gives the same value since the initial and final states are the same. In that last example, we were looking at two different chemical reactions. Hess's Law also applies to physical processes. So the enthalpy for the reaction of going from gaseous water to liquid water, we can look at we know the enthalpy that hydrogen plus oxygen to give us gaseous water. We know the enthalpy change for hydrogen plus oxygen to give us liquid water. So to look at going from gaseous water to liquid water, right, condensation, we would just need to, here's my elementary reaction number 1, elementary reaction number 2. This is my net equation. So I need my H2O gas on the left. And if we look for that in either of my two equations, I'm going to start going skim, skim, skim. Oh, here's my two H2Os, but it's on the right. So I need to flip this reaction. So I'm going to rewrite it, and I'm going to say 2H2O arrow 2H2 plus O2. And then I'm going to rewrite this delta H as a positive 483.6. So this is just saying that I'm going to decompose my gaseous water into hydrogen and oxygen gas. So I'm going to just cross this off here since I rewrote it. I flipped it. So therefore, I'm flipping the sign. Then I'm going to go, okay, where's my H2O liquid? It's on the right of the arrow. Oh, it's on the right of the arrow in our elementary equation number 2. So let's see if we can cancel out everything to just have our 2H2O gas, which right now it's on the left. Good. My H2O liquid on the right. Good. Oh boy, so we don't have any other pieces in our net. So let's make sure everything else cancels. I have H2O, two H2s on the left. So I'm going to circle this. And I have two H2s on the right, so they cancel each other out. I have one O2 on the left, one O2 on the right. They cancel out. And I have nothing else. So how would we find our delta H? Well, we just add up our elementary H's. So if I have a positive, and let's type this into our calculator here, positive 483.6 kilojoules plus a negative 571.7 kilojoules, and I should get a delta H of negative 88.1 kilojoules. Sometimes when using Hess's law, it's helpful to represent enthalpy data schematically in an energy level diagram. In these drawings, the various substances being studied, like the reactants and the products in a chemical reaction, for example, are placed on this arbitrary energy scale. And we can see that right here as energy increases. And we have two different equations here. These diagrams can give us a visual perspective on the magnitude and direction of enthalpy changes and show how the enthalpies of the substances are related. So here we're showing two examples of Hess's law that we discussed just earlier. Here we have elements carbon and oxygen. We can see are at the highest enthalpy, and the reaction of carbon and oxygen to form carbon dioxide lowers the enthalpy by 393.5 joules. So when we combine to form these, we can see carbon dioxide, it is an exothermic, it is lowering that enthalpy. This can occur in either a single step, like right here on the left, it can happen just in a single step, or we can see on the right here, it can happen in 2 steps. It can first form carbon monoxide and then continue on to form carbon dioxide. And Hess's law just shows us that that first step, we can calculate the energy it takes to create carbon monoxide. And then we can see that to go to carbon dioxide is, we would be able to subtract our H2 minus H1 to get H3, which this is what it's showing us here. The energy is still the same. It doesn't matter how we get there, whether it's in 1 step or 2 steps. Same with this one. To The mixture of hydrogen and oxygen gas is at the highest enthalpy, and both liquid and gaseous water have lower enthalpies, with the difference between the two being the enthalpy of vaporization. We can see right here, obviously it's gaseous, so that's vaporization versus this is in liquid form. And we can either go right from hydrogen, oxygen, gas to liquid water, or we can go in 2 steps, and we can see that these 2 steps equal the 1 step. If I didn't know what this enthalpy difference was, I could take step 1 minus step 2 to get this one. If I didn't know what this one was, I could take I just did that one. If I didn't know what this one was, I could take this guy minus this guy. If I didn't know what this one single step was, I could add these 2 together. So there's all different ways we can get there. Hess's Law tells us that we have a state function here, and that we can add or subtract enthalpies of reactions to find our delta H for the overall process. Let's look at a few examples. So here I have elementary reaction number 1 and elementary reaction number 2. I want to get, this is my net, my target equation. I want to get P4 on the left plus 6Cl2 to create 4 PCl3 in liquid form. We want to find out that enthalpy for this reaction. Now here's enthalpy for 2 other elementary reactions that we were given. And again, we could find these in the back of our book in the appendix. These are known standard enthalpies. So let's try to get to this one. So the first thing we need to do is, by no other reason than it's just listed first, we want P4 on the left. So let's find P4. Oh, here it is. P4 is on the left in our elementary reaction number 1, which is great. That's where we want it. So I'm just going to rewrite this number 1 just the way it is. P4 plus 10Cl2 creates 4 PCl5. Great. Next, I need chlorines on the left. Well, I've got chlorines on the left on both of them, so I'm just going to skip to my product. I want PCl3 on the right. PCl3. Oh, here we go. PCl3 is right now in elementary reaction number 2, but it's on the left. So we definitely need to flip this reaction. Also notice that I want 4 PCl3, 4 moles of it. Right now I have 1 mole of it. So not only do I need to flip my reaction to get it where I want, I also need to times it by 4. So let's do that. First, I'm going to multiply everything by 4, just because that's easy to do right here. 4, 4, and let's see, I don't want that to get confused. 4. But remember, whatever I do to this, I have to do to my delta H. So let's do that. Negative 123.8 times 4. And remember, since I'm flipping it, I'm also changing the sign. So this is going to become positive 495.2 after I flipped it and multiplied it by 4. So let's rewrite what we just did. We've got 4 PCl5 would be on my left now, and these 2 are going to be on my right to give me 4. Oh, I'm going to write it over here so that it's to the right of this arrow. We don't get confused. 4 PCl3 plus 4 Cl2s. And my delta H for this first one, negative 1774.0. Delta H for the second one we just found was plus 495.2. All right, now let's see if this gets us our target equation. We need P4 plus 6Cl2 to give us 4 PCl3. All right, let's see if we have anything that can cancel out. Notice I have 4 PCl5 on the left, 4 PCl5 on the right. Good. We want those to cancel out. We don't have that in our net equation here, a target equation. Let's see here. I've got P4, which is good on the left. I've got chlorines and chlorines. I'm going to come back to that one. On the right side of my arrow, I've got 4 PL3s, good. Now notice I have 4 chlorines on the right and 10 chlorines on the left. Well, we're just going to simplify. If I get rid of 4 chlorines on the right, that means I need to subtract 4 chlorines on the left. So 10 minus 4 gives me 6, which is good. That's what I want. So now we just need to sum up, because Hess's Law said we can sum up our delta H's. So I'm going to do negative 1774.0 plus 495.2 to give me a delta H of negative 1278.8 kilojoules. And this was a multiple choice question. So it said use Hess's Law to find what delta H is. And we can say, oh, there we go. There's our answer. Let's look at another example problem. We want to calculate delta H for the thermite reaction given the following data. So here's our target. Here are 2 elementary reactions that are given, that are known. The creation of aluminum oxide and iron 3 oxide. But I want this reaction. So I'm going to just write this underneath here. Push this up. My target, I want 2 aluminum plus Fe2O3 to give me 2 Fe plus Al2O3. All right. So I'm going to start, again, this is my target. And this is my elementary number 1 and number 2. We need to manipulate those to get what I want. So because it's number 1 listed first, I need 2 aluminums on the left. Let's look at number 1. Hey, 2 aluminums on the left. Great. I need Fe2O, so we're going to leave number 1 as it is. Fe2O3 I need on the left. Fe2O3 on the left. Oh, here it is, but it's on the right. So I need to flip number 2, which means I need to flip its sign to positive. All right, by doing that, let's see, or let's just keep going. I need Fe on the right, which if I flip this, I will have Fe on the right, and Al2O3 on the right. Al2O3 is on the right. So let's rewrite number 1 and 2 to see if that gets us where we need. All right, a line under here. Also, I'm not sure that says minus, it should say plus. Okay, so we're going to leave number 1 alone. So we've got 2Al plus 3 halves O2, Al2O3. You know how I know it was a plus? Because on the left here, if I had 3 halves of O2, that would give me 3 times 2 is 6, 6 divided by 2 is 3, and I have 3 O's on the right, so that would make it balanced. And then number 2, I flipped this, so I have Fe2O3, 2Fe plus 3 halves O2. And then my delta H here, we left the same, negative 1669. And delta H here, I flipped it, so it's plus 822.2. So now let's see if we can cancel anything out and get to our target equation. Okay, we've got our 2 aluminums. Good. We've got our Fe2O3. Good. We've got our 2Fe. Good. We've got our aluminum oxide. Good. And then notice I have 3 halves oxygen on the right and 3 halves oxygen on the left. They cancel out. Sweet. Okay. Now all we need to do is add our delta H's. So negative 1669 plus negative 822.2. So our enthalpy to create our target equation is negative 2491.2 kilojoules. Let's try another example. So given this data, what is the delta H for this reaction? So here's our new target. We have iron oxide plus carbon monoxide react to form carbon dioxide and iron. Well, here are three reactions that we do know. So how do we get to this from there? Why don't you pause the video and see if you can manipulate these? All right, let's look at this. Well, the very first compound that I want on the left is FeO. So where do we see FeO in our different elementary reactions? FeO, right here. So FeO right now is on the right. I want it on the left. Also notice that this reaction has 3 moles of FeO being produced, and I only want 1 mole of FeO. So I need to flip the sign, and I need to divide everything by what? By 3. Okay, so let's rewrite this, this third reaction. So I'm going to flip it and divide it by 3. So I'm going to have 3 divided by 3 divided by 3 gives me 1 FeO, plus I have 1 here, but I divided by 3, so 1/3 CO2. And that's going to give me, again, I divided each of these by 3, so now I'm going to have 1/3 Fe3O4 plus 1/3 CO, and that's going to give me a delta H of, I'm going to flip my sign, so negative 38 divided by 3. What does that give us? Negative 38 divided by 3. Negative 12.7. Negative 12.7. Okay, so we redid number 3, so I'm going to just process off because we have rewritten number 3. Next, I'm going to go, okay, we need CO on the left. Well, right now I've got CO on the right, and I've got some COs on the left, but that one gets a little hairy, so we're going to skip that one. Let's see if we can find CO2 on the right. Right now I've got CO2 on the left and CO2 on the right. So again, a little hairy, let's skip it. We need Fe on the right. And there's Fe. Notice it is on the right, which is great, but what's wrong with it? I want 1 mole of Fe, and here I have 2. So I can leave this in the correct format. I just need to, on the right-hand side, which is good, I just need to divide by 2, right? 2 divided by 2 will give me 1. So let's rewrite reaction number 1, dividing everything by 2. So I'm going to have 1/2 of Fe2O3 plus 3/2 of CO to give me 2 divided by 2 is 1 Fe plus 3/2 of CO2, and that gives me a delta H of negative 28 divided by 2, negative 14. Oh, I should have known that. Negative 14 kilojoules. All right. Now, let's just leave reaction number 2 the way that it is and see what that gives us. So I'm just going to write down number 2, 3 Fe2. Actually, I'm not going to, because I just noticed something here. Because if I write down, if I use elementary reaction number 2, I'm going to have Fe2O3 on the left, and I don't want Fe2O3 on the left. I'm going to need that to cancel. So I don't have Fe2O3 at all in my target reaction. And right now, when I flipped this, or when I wrote down number 1, I have half. So in order to cancel out, I need half of Fe2O3 on the right. So how do I go from 3 to 1/2? Well, I think we need to divide everything by 6, right? 3/6 is equal to 1/2. Divided by 6, and we need to flip. That would make sense. Okay, so we're going to flip this. So we're going to say divide by 6. So this is 1/6 of CO2 plus 2/6 of Fe3O4. Give me 3/6 of Fe2O3 plus 1/6 of CO. That'll give me a delta H of, we're going to flip that sign, so it'll be a positive 59. 59 divided by 6. 9.8. Okay. Let's see if we get our target equation here. Well, we've got FeO, the CO, we've got a couple different COs. We're going to come back to that one. Let's see if we've got our Fe, good, plus we've got CO2s in a couple of spots. So we're going to have to do some subtracting here. All right, let's find commonalities. We've got 1/2 of Fe2O3 and 3/6, which is 1/2 of Fe2O3 on the right. So we can cancel these out. What else do we need to cancel out? These Fe3O4s. I've got 1/3 of Fe3O4 and 2/6, which is 1/3, reduces. Cancel those out. All right, now let's look at CO2s. So I need CO2 on the right. I only need 1 CO2. Here I've got 1/3 of a CO2 and 1/6 of a CO2. So what would that equal? Well, 1/3 is equal to 2/6, right? So 2/6 plus 1/6 is 3/6, which is 1/2, correct? So I've got 1/2 of a CO2 that we're going to subtract from both sides. So 3/2 minus 1/2 is 2/2, which is equal to 1 CO2. Good. CO2. And then the only thing we have left here is our COs. Let's look at that. I've got 1/6 of a CO and 1/3 of a CO. So 1/3 is equal to 2/6. 2/6 plus 1/6 is 3/6. 3/6 is 1/2, correct? So I need to subtract 1/2 of a CO. So 3/2 minus 1/2 is 2/2. 2/2 is equal to 1. Phew! So we cancel those out, and then the CO is going to come right on down here. That was a tricky one. Now let's add up our delta H's. Negative 12.7 plus negative 14 plus 9.8. Negative 16.9 kilojoules to get our target equation.